Space Telescope Institute from Baltimore. Amaya is interested in studying everything that is flying in space in our galaxy, small objects like Oumuamua and other stuff, and also debris disks and everything that has to do with that. And today she'll be telling us about the interstellar object and their potential role in planet formation. Thank you, Amaya.
Thank you. Thank you for inviting me. So, let's start. So, I'm going to be talking about the interstellar objects, but I will start my talk with disks, because this is, I guess, how I started my career, but also everything is related, right? So it's like a storyline. So back with Spitzer, that unfortunately they just shut the mission down a few days ago, right? So back with Spitzer and also with Herschel, we've done surveys of debris disks. These are disks of circumstellar dust that surround main sequence stars. And one of the things that we have found is that, is there a pointer? Okay, there's a pointer. One of the things that we have found is that debris disks are very common around main sequence stars. And for example, here you have some frequencies for A-type stars. It's around 30% of stars are surrounded by these dusty disks. And for lower mass stars, the percentage is a bit lower, but they are fairly common. One of the things that we have learned is that they are fairly common. And this circumstellar dust is not primordial. It's not coming from the protoplanetary disk, or it's not coming from the primordial cloud where the star was born. It's a second generation of dust. These dust particles are being produced. We think that the origins are planetesimal, that planetesimals are colliding with each other and are producing the second generation dust. So one of the things that we have learned from these surveys, from these debris disk surveys done with missions like Spitzer and with Herschel, is that these dust disks are very common. And because we think that the origin of these dust disks is this secondary dust, is these planetesimals colliding with each other, we think that this is evidence that planetesimal disks are common, that planetesimal formation is a robust process that can take place under a wide range of conditions, because these dust disks are present around stars with a wide range of stellar metallicities, and also stellar luminosities, right? So one of the things that we've learned from debris disks is that planetesimal disks are common. And one of the things that we have learned from dynamical simulations is that the ejections of these planetesimals is also a fairly common process. In here, for example, you have 3 planets embedded in 2 swarms of planetesimals, one outside the orbit of the planets and one inside the orbit of the planets. And commonly, this is what happens once the planetary system evolves. The planets evolve in such a way that these planetesimal disks are clear. In the solar system, for example, there is evidence that our planetesimal belts were much more populated in the past, and that what is left behind is just a tiny fraction of what was initially. So, of course, the efficiency of this clearing of planetesimals is going to depend on the architecture, but dynamical simulations indicate that for a wide range of planetary architectures, this planetesimal clearing is very efficient. So on the one hand, we are saying that planetesimals are common, planetesimal disks are common. On the other hand, we know that the dynamical evolution of planetary systems tend to lead to the clearing of these planetesimal belts very efficiently. So this led to the conclusion that the interstellar medium must be filled with planetesimals. And however, 10 years ago, I guess, with Avi, we look at this, because this seemed to be at odds with the fact that we had not detected any planetesimal coming through the solar system. And if these free-floating planetesimals, ejected planetesimals, were very common, it was expected that one of these planetesimals will be detected as a hyperbolic comet, right? A comet with a clearly interstellar origin. And this was not the case prior to 2017. So we look at this, we address this apparent tension between the observations and the expectations, and we got to the conclusion that probably the number density, based on what we knew about the star formation and planet formation, the frequencies of these processes to happen, we got to the conclusion that probably the number density of this interstellar, free-floating interstellar material was too low, and that it was okay that we had not detected any interstellar comet, because probably to detect one, we will require surveys, deep surveys like those in the LSST area and beyond. And so that's where we left it about 10 years ago, right? But there was another thing that we looked at, and it was at the possibility of exchanging material when the stars, because if you have these planetesimals that are being ejected from one system and into the interstellar medium, we look at the possibility of exchanging material between planetary systems, and we look at it in the context of an open cluster. And so one of the things that we did is that stars, as you know, are commonly born in open clusters. When the stars are in the open cluster, the relative velocities are small. They are about 1 kilometer per second. So the probability of transferring material from one planetary system to another is much, much larger than when the stars are in the field and the relative velocities are much higher. In that case, the probability of transfer is very low, but when you are in the cluster, and I can show you this simulation again, here you have two stars that are in the open cluster and they are orbiting the cluster, and these are some planetesimals that are being ejected from this star, and only one gets transferred. And we are looking at these orbits that are nearly parabolic orbits, so they are chaotic orbits. And we found that the probability of transferring this material that was being ejected from one system, the probability of transferring to another system inside the cluster before the cluster disperses, is much larger. It was many orders of magnitude higher than previously thought if you consider this type of orbits. And the reason why we thought this was interesting is because the time when the sun was embedded in the open cluster, we think that the sun was born in an open cluster that might have lasted between 130 and 530 million years. And during this period that the sun was still embedded in the cluster, there is evidence that there was a lot of dynamical activity in the solar system. The heavy bombardment happened, all this planetesimal clearing happened of the asteroid belt and the Kuiper belt. And so we think that there was, during this period where the sun was still embedded in the cluster, there was all this dynamical activity that could have cleared those planetesimals, right, into this type of nearly parabolic orbits. And it was also a time where there was already evidence, based on the zircons, there was already evidence of liquid water near the surface of the Earth. So there is the possibility that sun material, if there is liquid water near the surface of the Earth, there is always the possibility that life could have already, I mean, we don't have any evidence of life back then, but because the first evidence of life happens much later, the first microfossils, but if there is evidence of liquid water near the surface, there is the possibility that life was already present. And during that time, there is evidence that there was this dynamical mechanism that could have exchanged material between these planetary systems from the solar system to other planetary systems in the cluster, and also from other planetary systems in the cluster to our solar system. So this was an interesting idea that you have all these planetesimals are common. You have mechanical, you have dynamical processes that clear these planetesimals efficiently, and that when the stars are still embedded in the clusters, you can actually have this material being transferred from one system to another. Of course, once the cluster disperses, this material, the efficiency of transferring material from one system to another one decreases tremendously, but recently there was this wonderful suggestion by Siraj and Loev. Ah, there you go. So that suggested that maybe even after the cluster dispersed, you can still transfer biologically interesting material, right? If you have some of these planetesimals crossing on Earth grazing orbits, right, and capturing some of the microbes that might be in the atmosphere and then fly away. They just fly away. So there is still the possibility that some of this material could be transferred using these interstellar planetesimals that are being, are free floating. There is still a possibility that the material could be transferred even after the cluster disperses. So, and then we got Oumuamua. So Oumuamua was the first interstellar comet that was detected. I mean, it's not a comet. It was the first interstellar object that was detected in the solar system, and we were surprised by the fact that it was detected with pan-stars, because pan-stars did not go as deep as we thought we would need to go to detect this object. And we got actually very lucky, because this was a very small object, relatively speaking, because comets generally are like a kilometer in size, but Oumuamua was about 100 meters in size. But it so happened that we detected when it was very close to it passed really close to the Earth, and we were able to detect it when it passed close to the Earth, and it was on its way out already from the solar system. So when Oumuamua kind of got us by surprise, and it's kind of ironic because we had been waiting for one of these interstellar comets, but then when we got it, we were kind of surprised because we couldn't figure out where it was coming from, and it left many open questions. Its visit was very brief, and it was subject of intense observational campaigns, but it left many open questions, and I'm going to tell you about a few of them. So the main question of Oumuamua is the origin. And so, as I said, one potential origin could be that it's